Since the Apollo era, landing on the moon has always been incredibly difficult. But doing it with Starship HLS in this century, that's an entirely different level of challenge. It sounds ironic. Technology has advanced so much, yet the mission is now even harder. And the reason is simple. No one has ever tried to land something as tall as a 15-story building on another world before. SpaceX now faces hundreds of engineering problems with no existing blueprint, no prior example to follow. That raises an interesting question. Why not build something smaller, something less complex, something that fits the harsh physics of the lunar surface? That's where the idea of a mini Starship comes in. So, what exactly is mini Starship? And could it make lunar missions far more practical than ever before? Let's break it down in today's episode of Alpha Tech. After winning the HLS contract for Artemis 3, Elon Musk directed SpaceX to build something truly revolutionary, the world's largest lunar lander, the Starship HLS. When fully developed, its habitable volume will exceed 600 cubic meters, roughly 135 times larger than the Apollo lunar module, which had only about 4.5 cubic meters of space. Elon Musk once described her as a planet colonizer class rocket. The magnitude of that task makes every other space transport task trivial. And he's not exaggerating. With that kind of volume, the HLS could carry hundreds of tons of cargo to the moon, or potentially 20 to 30 astronauts in a single mission, even though the Artemis configuration only includes 4 seats. But here's the problem. Those headline numbers are mostly theoretical. Turning them into reality is a whole different story. Take Artemis 3 as a concrete example. Before an HLS ever touches the lunar surface, SpaceX would need dozens of tanker flights to top off a Starship depot in orbit, essentially a gas station in space. Only after that depot is filled could an HLS rendezvous, refuel, and have the propellant margin to reach lunar orbit and attempt descent. That sequence is intrinsically risky. You're asking multiple large spacecraft to meet and transfer huge quantities of cryogenic propellant while all of them are traveling at orbital velocities, roughly 26,000 kilometers per hour. Docking and propellant transfer in that regime is non-trivial. Any failure in a rendezvous or a leak in a tanker would leave the HLS short of fuel and the whole mission in jeopardy. Say they clear that hurdle. The next set of problems is just as daunting. The HLS is enormous, about 52 meters tall with a 9-meter diameter, essentially a 15-story building in a vertical tin can. No one has ever tried to land something that tall and that wide on another world. And that's where things get tricky. With a height-to-width ratio of more than 5:1, the vehicle is inherently top-heavy, and on the moon, where gravity is only 1/6 that of Earth, that becomes a serious stability issue. In a conventional Starship design, the lower section houses the engines and the main propellant tanks. But by the time the HLS begins its descent, most of that propellant is gone. That means the bottom becomes lighter than the upper sections, shifting the center of mass higher and making the entire vehicle more prone to tipping over, especially on uneven terrain. So a lot will depend on the landing legs. They'll need to support a vehicle weighing somewhere between 200 and 250 tons during touchdown, absorb the impact, and still remain stable even if one leg sinks into a soft or uneven patch of lunar soil. You can see how the list of problems starts to multiply quickly. Each of these challenges requires new modeling, new materials, and new engineering solutions. It's no exaggeration to say this is one of the hardest design puzzles ever faced by rocket engineers. But it also raises an obvious question. Why not build something simpler, smaller, like a miniature version of the Starship HLS? So here's the idea. Instead of using the massive Starship lander, SpaceX could go for a downsized version, a mini Starship. Around 6 meters wide, 30 meters tall, and weighing just about 50 to 80 tons when it touches down. Even at that size, it could still carry 4 astronauts, matching the crew requirement for Artemis 3, and because it's lighter, the total liftoff mass would drop to around 800 to 1,000 tons when fully fueled. That alone would take a huge load off the super heavy booster, allowing it to fly higher, farther, and still return safely without going expendable. It would also cut the number of tanker flights needed for orbital refueling nearly in half, speeding up propellant transfer and reducing boil-off losses. And with 6 engines, 3 vacuum and 3 sea-level Raptors, this smaller vehicle would still have enough performance to reach lunar orbit and land safely on the surface. And when it comes to landing, the mini Starship has a huge advantage. It's simply easier to pull off. Think about it. Smaller size means less torque acting on the ship when landing on a tilted surface, say 10 to 15 degrees. Its center of gravity is around 8 to 10 meters above the base, compared to 15 to 20 meters on a full-size Starship. That lower profile makes it way less likely to tip over, basic leverage physics. Plus, because it's even smaller than a Falcon 9, the landing legs are a no-brainer. SpaceX could literally take Falcon 9's design, upgrade it, and it would work perfectly. 4 foldable legs, simple and sturdy, providing about 5 square meters of contact area. That's enough to keep it from sinking into lunar regolith. Now, compare that to the regular HLS version. That monster needs 6 massive landing legs, heavier, wider, and way more complex to design and deploy. All of that adds up. More mass, more complexity, and more risk during touchdown. The mini Starship, on the other hand, is lighter, easier to balance, and with its onboard LiDAR and radar scanning the terrain, the chances of tipping over or landing on uneven ground drop dramatically. So, yeah, even though it's half the size, it's probably 10 times easier to land safely. And here's how it would actually do it. As it approaches the lunar surface, the ship performs a flip maneuver to orient itself vertically. Then, instead of using a sea-level engine, it fires up a single Raptor vacuum, since the moon's atmosphere is practically a vacuum. When it's about 200 meters above the ground, the thrust gradually throttles down from 50% to around 10 to 20%, producing roughly 80 to 130 kilonewtons of thrust, just enough to slow the descent from a few meters per second to almost zero. Of course, its advanced navigation system would have already scanned the lunar South Pole terrain, picking out the flattest spot, free of rocks and craters. Then, the 4 landing legs unfold, while the RCS thrusters kick in to keep the vehicle balanced, and, of course, to clear away the cloud of lunar dust blasted by the Raptor. Finally, the mini Starship touches down softly, completing a safe landing, ready for astronauts or cargo to begin their lunar mission. And with up to 50 tons of payload capacity, it could still deploy experimental machinery, collect lunar samples, and even serve as a temporary habitat for a crew staying 1 to 3 months, not so different from the full-sized Starship. Pretty wild, right? If you think this idea actually makes sense, drop a 1 in the comments. But as good as this idea sounds, it still faces some serious challenges. First, payload capacity. A mini Starship could only carry about 20 to 50 tons, far less than the 100 to 150 tons of the full-size Starship. That's not enough to haul all the equipment, habitats, and power systems needed to build a real lunar base. Second, with a smaller propellant load, its range and mission flexibility would be limited. It might handle short surface missions, but round trips between lunar orbit and the surface, that's pushing it. Third, cost and complexity. Designing, testing, and building a brand new variant would eat up extra time and money, something NASA and SpaceX can't really afford right now, especially when the current Starship is already optimized for multiple roles. And finally, versatility. Sure, a mini Starship might be great for lunar landings, but it wouldn't fit SpaceX's bigger goals, like carrying massive cargo or sending crews to Mars. So even though the idea makes lunar missions easier, it doesn't really move the needle towards SpaceX's ultimate vision, building Moonbase Alpha and going interplanetary. In fact, the idea of a smaller Starship isn't new at all. It actually came from Dr. Robert Zubrin, founder of the Mars Society and the man behind the famous Mars Direct Plan. Back in 2019, during the International Astronautical Congress, and again in his 2025 proposals, Zubrin discussed with Elon Musk a concept he called the mini Starship, or starboat. It would be about 58% the size of the original, roughly 5.2 meters wide and 25 to 30 meters tall, with a full mass around 260 tons, powered by just 2 Raptor engines instead of 6. The goal? To create a cheaper, more reliable vehicle for early Moon and Mars missions, one that wouldn't depend on complicated ISRU infrastructure. It could even be launched by a Falcon Heavy or a full-size Starship booster, but Musk turned it down. He wanted to focus on building one universal vehicle, a do-everything Starship. instead of splitting resources across multiple versions. Following Zubrin's proposal, another standout idea came from Tim Dodd, better known as the everyday astronaut. He's one of the most respected space communicators out there, known for breaking down rocket science like no one else. Recently on X, Dodd suggested a new variant called the stubby Starship. It's basically a shorter, chubbier version of the original, around 30 to 35 meters tall instead of 50, but still 9 meters wide. Dodd argued that this stubby design could still fly on today's Super Heavy without major changes, making it perfect for early lunar missions as a kind of mid-sized starship, easier to produce and capable of carrying around 80 to 100 tons of payload. Not sure if Elon's ever seen that idea, but honestly, it's a pretty clever one. It's not clear whether Europe took inspiration from Zubrin or Dodd, but one notable example from across the Atlantic is actually coming from the European Space Agency. This isn't just a paper concept, it's a real development program. At the 2025 International Astronautical Congress in Sydney, ESA announced a €40 million, about $47 million contract with the Italian company Avio to design a reusable upper stage for future European rockets. It doesn't have an official name yet, but from the renders, you could easily call it a mini Starship. It looks strikingly similar to SpaceX's Starship, just scaled down. The vehicle stands about 36.5 meters tall, with a smaller diameter, 4 flaps for aerodynamic control, and an engine-powered landing system. But instead of a liquid booster like SpaceX's Super Heavy, this one rides on a solid fuel first stage, similar to Avio's Vega C rocket. The goal here is to lower launch costs and make Europe more independent in spaceflight, focusing on powered descent and advanced composite materials. Still, its smaller size limits payload capacity to around 20 to 30 tons to low Earth orbit, and critics argue it borrows a bit too much from SpaceX's playbook. So the question floating around forums and social media is this truly innovation or just Europe's own Starship clone? To answer those questions, we need to go back to NASA's early days, a time when some of the wildest ideas in spaceflight history were born. And among them was one that stood out above all, a concept for a massive spacecraft called Nova. The Nova rocket was envisioned to carry between 10 and 20 astronauts at once, along with 75 to 100 tons of equipment and supplies. These gigantic landers would touch down entirely on the lunar surface and then launch back into orbit without leaving any hardware behind. A bold plan aimed at building permanent outposts, not just short visits. All of these ahead-of-its-time ideas came from Wernher von Braun, the legendary rocket engineer who played a key role in NASA's Apollo program. And it's no surprise that Elon Musk has often cited von Braun as one of his greatest inspirations. When you look at Nova's original specifications, they sound strikingly familiar, almost like an early blueprint of what Starship has become today. All of this is true. You can actually find the official Nova launch vehicle documents on NASA's own archives. Take a look. They were all publicly released back in 1963 and 1964, and the level of detail is mind-blowing. NASA engineers even drew out step-by-step diagrams showing exactly how the vehicle could be built. According to those early designs, Nova was a super heavy-lift launch vehicle, a 3-stage rocket that stood slightly taller than Saturn V, but was much wider in diameter. While Saturn V's first stage measured about 10 meters across, Nova's enormous first stage would stretch to 15 meters, providing space for gigantic fuel tanks and a massive cluster of engines. That first stage was planned to use 8 F1 engines, the same type that powered the Saturn V, but grouped together in an even larger cluster, producing an incredible 14 million pounds of thrust. And the second stage, just as impressive. It was designed to carry 8 J2 engines, generating more than 1.8 million pounds of thrust. The third stage, also powered by J2, or even larger M1 engines in some variants, served as the integrated propulsion unit for the lunar lander itself, not a crew compartment, but the engine and fuel backbone that allowed the entire 150 to 200-ton lander to descend and ascend intact. With that kind of power, Nova could carry payloads and crews far beyond what Saturn V was capable of. Its projected capabilities included landing 10 to 20 astronauts on the moon in a single mission, along with 60 tons or more of cargo, everything from habitats and rovers to life support infrastructure, all housed in a massive, self-contained lander mounted atop the third stage, where the crew lived, worked, and returned using the same vehicle that brought them there, without ever needing orbital refueling or rendezvous. But if the Nova concept was so brilliant, why was it canceled? The answer is surprisingly simple. The Nova project was officially scrapped in 1964, not because of a lack of ambition, but because NASA simply couldn't meet all three critical demands: time, cost, and technology. President Kennedy's goal was clear: land a man on the moon before 1970, a race driven by political and technological rivalry with the Soviet Union. But Nova, with its massive diameter, too many engines, the need for new factories, transport canals, and tens of billions of dollars in funding, would have taken at least 8 to 10 years to develop, far beyond the political deadline. Meanwhile, the Saturn V was smaller, simpler, and built on proven technology from the Jupiter program. The F1 and J2 engines were already showing success in early tests. And most importantly, NASA adopted the lunar orbit rendezvous strategy, separating the main spacecraft from a lightweight lunar lander that would meet in lunar orbit. This new approach reduced launch mass by around 70% compared to Nova's direct ascent method, making the entire mission far more practical. Even Wernher von Braun, the father of Nova, publicly supported LOR in June 1963, declaring, "It's the only way to make it before 1970. And so, NASA shifted all its focus to Saturn V, turning an ambitious dream into a realistic plan. And just 5 years later, Apollo 11 made history by landing humans on the moon. In short, Nova wasn't a bad idea. It was just too far ahead of its time. That's why Elon Musk could absolutely bring it back to life in the form of Starship Nova, to make lunar landings easier than ever before. And in many ways, this time it would be much more doable, because Starship already surpasses what Nova was ever designed to achieve. Its fully reusable two-stage architecture stands out, with the Super Heavy booster as the first stage, powered by 33 Raptor engines. Together, they generate more than 16 million pounds of thrust, easily surpassing the Nova's theoretical 13.9 million pounds from its 8 F1 engines. The second stage, Starship itself, carries 6 vacuum-optimized Raptors, producing 2.8 million pounds of thrust, more than double the power of Nova's second stage, which relied on 8 J2 engines generating about 1.86 million pounds. And in the future, this upper stage could even use up to 9 Raptors, making it even more powerful. The only major change would be structural instead of the original 2-stage configuration. Starship Nova would feature a 3-stage design. And interestingly, SpaceX wouldn't even need to add an adapter to dock a 3rd stage on top of the Starship upper stage, because that stage could actually fit inside Starship's massive payload bay. However, building an entirely new 3rd stage would take a lot of time, effort, and money. So instead, the idea is to use the upper stage of another vehicle, like the Centaur 3 used on ULA's Vulcan rocket, which could easily fit within Starship's enormous payload compartment. A Centaur stage, with its slender design and high-efficiency RL-10 engine, could provide valuable flexibility for lunar transfer or interplanetary missions. In fact, by clustering 4 RL-10 engines together, a modified Centaur upper stage could deliver around 96,000 pounds of thrust, quite an impressive figure by today's standards. However, when compared to the planned 3rd stage of Nova, powered by a single J2 engine, Centaur falls short. The J2, which also burns liquid hydrogen and liquid oxygen, produces far greater thrust, reaching up to 232,000 pounds. This large gap highlights the current limitations of upper stage technology when it comes to achieving the kind of deep space, heavy lift capability envisioned for Nova or a modified Starship. Moreover, even if the size and thrust match, there are still some major drawbacks. For example, Centaur and Starship belong to 2 different companies, ULA and SpaceX, and direct collaboration between them would be very difficult without a third party, like NASA, acting as a mediator. Moreover, to actually match or surpass Nova's ambitions, any potential 3rd stage added to Starship would likely need to go beyond the existing Centaur-class designs. That could mean reviving high-performance engines like NASA's shelved J2X, or exploring next-generation nuclear thermal propulsion systems, which NASA already has on its roadmap for future deep space missions. In general, a third stage could save a lot of money. Basically, it would be a smaller Starship without the heat shield, aeroshell, landing legs, or extra tanks, so it would cost a lot less to build than a full Starship/Super Heavy system. High delta-V missions aren't super common right now, so it might take a while before the investment really pays off. But with Starship's insanely low launch cost, demand could pick up eventually, even if it takes a few years. Government agencies like NASA and the U.S. Space Force are the main customers for high delta-V missions, like flying directly to geostationary orbit or heading to other planets. They might even help fund the development of this third stage. Aside from the upper stage issue, there's another crucial factor Starship would need to change to truly become a Nova Starship: its choice of propellant. As space agencies and private companies set their sights on building a sustainable human presence on the moon, the choice of fuel becomes a critical part of mission design. For lunar operations, hydrolox, the combination of liquid hydrogen and liquid oxygen, remains the most practical and efficient option, especially when considering future in-situ resource utilization. One of the moon's most valuable natural resources is its vast reserves of water ice, found mainly in the permanently shadowed regions near the lunar poles. This ice can be extracted, refined, and split through electrolysis to produce both hydrogen and oxygen, allowing hydrolox fuel to be manufactured directly on the lunar surface. That capability would drastically reduce the need to haul fuel from Earth, cutting mission costs and enabling long-term lunar operations. In contrast, methane-based engines like SpaceX's Raptor are optimized for Mars missions, where methane can be synthesized from atmospheric carbon dioxide and subsurface ice via the Sabatier process. But since the moon lacks a carbon-rich atmosphere, producing methane there simply isn't practical. Without the ability to generate local methane, lunar missions relying on Methalox engines would face major logistical challenges for return trips and surface operations, as every drop of propellant would have to be transported from Earth, an extremely costly and limiting approach. For that reason, upper stages and landers intended for sustained lunar activity would be far better served by hydrolox propulsion systems. These engines not only deliver higher performance in the vacuum of space, but could also one day be refueled directly on the moon. Integrating hydrolox-based propulsion into Starship's architecture, or pairing Starship with a hydrolox upper stage for lunar missions, would align far more closely with the long-term vision of a self-sufficient lunar infrastructure and permanent human outposts on the moon. Finally, converting Starship into a Nova-class heavy-lift transporter could bring significant advantages for deep space missions, particularly in terms of payload capacity and mission simplicity. A Nova-class Starship variant, whether through increased thrust, a third stage, or both, could deliver 68 tons or more to translunar injection orbit in a single launch, without any in-orbit refueling. That capability instantly outperforms NASA's Space Launch System, which currently delivers a maximum of about 38 tons to TLI. This leap in capability would greatly streamline lunar missions. With just one launch, Starship could carry larger, fully equipped lunar landers, heavy cargo, and multi-astronaut crews, achieving the goals of the original Artemis missions and beyond in far fewer flights.